So this might be a little bit grab-baggy, but just want to kind of weave in all of the different places where you may have seen complex variables in physics, and we'll talk about unifying them and some of the theory behind complex analysis or complex valued functions. So this is the super basics, is we have the complex plane, and we have a complex number that can be described as a point in the complex plane. And if we want to, we can represent that in so-called rectangular form, where it's got a real part, how far down the real axis you walk, and then an imaginary part, how far up the imaginary axis you walk. Or, and this is going to be increasingly useful, we can describe this in so-called polar form. So z equals r ei theta. And it turns out that you guys now know and love Euler's formula, where you can turn e to the I theta into sine and cosine. So this would be r cos theta plus I r sine theta. And then really clearly you can identify that r cosine theta is A and r sine theta is B. Right? So you can switch back and forth, toggle back and forth in between these as needed. So the question is, why would you do this? And the answer is a lot of reasons. So sometimes for convenience, sometimes for a little bit more necessity, and sometimes there are some amazing tricks that you can do with this. So one example is traveling waves. You guys are used to seeing E, for instance. Let's say I have an electric field that's moving in time, Ex of t, that's E naught, maybe sine omega t minus kx plus some phase, and then it's got a polarization. Let's just say it's polarized in the k direction. And then likewise, it's got a magnetic field. Turns out that this might be a little bit chunky, and we can express this more elegantly, the E and the B field of traveling, or any traveling waves for that matter, as e to the I, let's do it the same way we did it here, omega t minus kx, right? And that honestly is just, exponentials have more compact forms when we take derivatives and stuff like that. So you will see traveling waves expressed in complex values. And honestly, for that matter, that's really what's going on with Schrodinger's equation. So Schrodinger's equation, we have d by dt of a wave function is I. So that's the whole point, I guess. So we've got an I there, and then we've got h bar squared over 2m Laplacian psi plus v of r psi. All right, so this is the time-dependent Schrodinger equation. And clearly, because there's an I there, and we have, in this case, maybe it's in 3D, and it depends on time, we have this thing. And the game that you play with the wave function is you tell me a point in space and a point in time. So you tell me where and when. And then I give you a complex number. So this is a complex valued function. I'll say necessity. It turns out you can describe quantum mechanics in terms of nothing but real valued stuff, but I would just not recommend it. I think we're, yeah, what have I done? Yeah. So this is more necessity. Fundamentally, quantum mechanics is a complex valued theory. Here's one that's more in the parlor trick kind of realm, is imagine that I had a pendulum, and my pendulum was in Moscow, right? And the Earth is spinning. I hope the Earth is spinning that way. And I zoom way, way in, and what you're used to analyzing in waves and optics and oscillations and mechanics is the simple harmonic oscillator, and usually you even put it in a small angle approximation, and you don't worry about the fact that it, in and of itself, is in a rotating reference frame. So if you decide that you do want to talk about the fact that this is on a rotating platform, namely planet Earth, what you end up is including the Coriolis Force. So you get ma equals mg, and we'll just put vector hats on these. So we have F equals ma, and we have force of gravity, we have force of tension pointing along the rope, but then we get this fictitious force, which you might be working on now in classical, if you're in classical. That's given by this. So this is the so-called Coriolis force. Right? Fictitious force that's an artifact of you being in a rotating reference frame. There it is. So let's say that you wanted to analyze this. Like this, we can do this, right, without that. Now you want to include this. And you put yourself in the XY plane. So I plug stuff in. And what I used to have, I've got X double dot and Y double dot. This thing is accelerating in the X direction and the Y direction. So we'll call that X and Y. Do that really badly, X and Y. So Z is still up and down. And I'll divide by M so we get some constants. We'll just clean things up preemptively. And because of this cross product term, what you'll get is y dot in your x equation of motion and your x in an x dot in your y equation of motion. So if you go through the Coriolis force and include it, what you end up with is coupled differential equations. Oh no. And the traditional way of solving this, and you may have actually seen this for the driven damped harmonic oscillator too, is to just use a clever chain of variables. Because what I can do is, instead of having two funky coupled differential equations of two different variables, I can have, and the x and the y make it really easy, I can just define a new complex variable that's x plus iy, right? And actually, we'll call it q. Q plus iy. And then these two coupled differential equations actually become one single differential equation. However, with they act on a complex variable. And what does this look like to me? Well, this looks like I got a q double dot term, and then I got a kappa q term, and then I've got this thing. It kind of looks like a single damped oscillator. And I'll put damped in quotation marks because the damping constant is complex. So you can compare this, for instance, to if you just remember the damped oscillator, you get something that looks like this. So really reminiscent of a problem that you've already solved. So that's one way of getting rid of the coupled nature of the Coriolis force pendulum equations, otherwise known as Foucault's pendulum. So that's Foucault's pendulum. So that seems like a cool parlor trick. And we actually know even how to deal with so-called complex damping. So I could write down the solution of this. So I'll say no, but what that really probably means is remind yourself of the damped oscillator and then just don't worry about the fact that beta is a complex number. So it kind of doesn't matter that beta is a complex number. And you can just write down the answer. So I omega zt. This would be in some sense me reaching into my DiffyQ textbook and pulling out the should have t's there, known solution. Okay. So this is easier to solve than that because we got rid of the coupling by introducing this variable. The last example is something that actually, when you paused this video and then you went back and you reviewed your 1230 damped oscillators, you actually said, wait a minute, there's another place where complex numbers showed up in my life. And that was in the transition from underdamping to overdamping. And this is just the normal simple harmonic oscillator. So I'm actually not even going to worry about small angle approximations, and I'm going to put a mass on a spring, and then I'm going to introduce a piece of cardboard on it, which introduces some damping. So the equation of motion for this is ma equals f. What's f? Minus kx. Actually, I should probably call this y. And then there's an mg that points down. You could change your coordinates to get rid of that if you wanted to, so don't worry too much about that. But then we also get this minus beta y dot, right? So, aha, this looks a lot like that, right? And the mg is just because I happen to draw this going in the vertical direction. So we have an equation that looks fundamentally like this. So you've got a double dot term, a single dot term, and a constant term. So we could do some shuffling, and we could make this look even more reminiscent of the thing we have up there. So you could get q double dot plus 2 gamma, kind of rephrasing and dividing, where gamma is this beta over 2, and then omega naught, which is k over m squared, or omega naught squared is k over m, equals 0. So this is the differential equation for a damped oscillator. This is the damping term, q. And I can solve this. And the solution to this has a square root, gamma minus omega naught looking term. So that's the damping out, so it's going to die out, and then we'll put the constants inside. So basically, I'm rewriting that. And actually, let me, instead of just rewriting this, let me rewrite this in terms of sines and cosines for fun. Just so, I don't know if we've talked too much about hyperbolic cinches, or hyperbolic sines and cosines. And this would be a good time to do that we have just these things that we defined for convenience when we took the beta term or b term and divided by 2m, and then we have omega damped. And this is the thing where all of the interesting stuff happens, omega squared minus gamma squared. Okay. So if you look inside of this omega damped, so what it's saying is that the natural frequency of the mass on a spring, so it's omega naught, if I stretch it and let it boing, if I introduce some damping, it's going to oscillate more slowly. So that doesn't really surprise anybody. But the thing is this is chosen in the hardware store. So this is the spring constant divided by the mass. And this is chosen by the amount of cardboard we use. So 4m squared. So that's really what this is. These are completely independent. So two different choices. This is the damping, and then this is the strength of the spring. There's no law that says that we can't choose a really wimpy spring with a really big piece of cardboard. So what that means is we could have the argument of the square root be negative. What happens if we have the argument of the square root be negative? Well, 10 years ago, when you first started learning about numbers, you just say, like, does not exist, and you wrote that on your homework. But now, what we can say is that's a totally valid solution. So no law against having omega naught squared be much, even just less is good enough, less than gamma squared. And so what we get is omega d is imaginary. And what happens if I have imaginary sines and cosines? Well, the physical content of that is this is what my oscillation looks like. I have this kind of envelope of e to the minus gamma t, and I wiggle back and forth, and then I die out. So this is underdamped. This is kind of what you would expect with the damped oscillator. Or we could have overdamped. And in this case, we never wiggle. We just kind of slink miserably towards 0 and never get there, or we get there at infinity. And it turns out that this is completely within the solution itself. There's no like separate mathematics that we have to do, because it turns out that if I have a complex, if I have an imaginary argument of a sine or a cosine, that's a hyperbolic sine or a cosine, and that does exactly that. So let's take an overdamped solution where gamma is greater than omega naught, and then we'll define this as I times, just pulling out the -1 through the square root, gamma squared minus omega naught squared. Right. So it's pull out a -1, and so we do get a real thing in there. You know, you can think about that as the complex part. Otherwise, calling this I times omega d. So then our solution for, again, overdamped system look like this. And then I would notice that if I have sine of I alpha for some real number alpha, this is a sinh. This is a hyperbolic sine. Likewise, cosine of I alpha, again for a real valued alpha, is a hyperbolic cosine. So these, in some sense, are my at least definitions. One possible definition of hyperbolic sine and cosine. And we didn't have to come up with a second totally new solution. So just knowing some properties of complex valued functions was really useful in that case. So these are places where you may have seen complex numbers and complex functions before. Again, it seems like a total grab bag. What we're going to do in the last unit of this class is go back and just talk about the theory of complex valued functions. And a couple of other tricks, including like the kind of coolest, but maybe in the modern era of computing, not as useful as it once was, trick of conformal mapping.